I'm Carol. I am a water resource engineer with the Center for Watershed Protection. Oh, there we go. This little guy here. I want to thank the Illinois River Watershed Protection for inviting me to speak here. Oh, there's a timer. That's great. I just noticed this. Inviting me to speak here, and all the previous presenters and everyone here. I am not from Northwest Arkansas. I am from Maryland originally, and so it's been great to hear everyone else's perspective and to see the different struggles and also advantages of stormwater management in this part of the world. So it's been really cool to hear everybody and talk to everybody. So just a little bit of background about the center. We are a nonprofit. We are based out of Maryland, but we have offices throughout the country. There's about 20 of us. It's a small but mighty staff. We kind of have 4 pillars in what we do. Our first is research, probably one of our smaller ones. We do research in much more applied research in terms of stormwater and watershed management. So we do things like the performance of biochar or a wood chip bioreactor or the impacts of salt in stormwater. And then we also do a lot of training. We do training on better site design, MS4 regulations, IDDE, and we also have a clean water certificate, which if you guys know what NGICP, the National Green Infrastructure Certification Program is, it's a great program that was created by WEF, and I think Seth had part in, or the first speaker yesterday had part in developing that program. The Clean Water Certificate is an entry-level training for green infrastructure construction and maintenance. It's very, very basic. It's kind of the stepping stone into NGICP because there is this growing need for stormwater infrastructure, but the lack of people understanding how to construct them and how to maintain them. And through time, we know that the correct construction and the correct maintenance of it really is vital to the longevity of a stormwater practice. The other pillar of CWP is membership. So we have the Center for Watershed Protection Association. Just like any other membership program, it's really just to connect with each other and network. And we have an online watershed library, and there's just a lot of resources, and we have an annual conference as well. So the part that I work the most in is this last one, which is Stormwater Services. It's much more like a consulting practice. We do a lot of guidebook writing. So we wrote the Virginia guidebook, which I think the Fayetteville and the Nashville one pulls a lot from. And we wrote the DC guidebook, the DOE one, which is different from what Henderson was talking about. He's DC Water, or his work was in DC Water, and I'll talk about that difference in a little bit. And we also write a lot of watershed plans for communities and for counties. And I do a lot of retrofit sites. I'll explain the retrofit idea later in my talk as well. In design and permitting, and construction, inspection, and we do a lot of plan reviews as well. And one of the things that I think the center is lucky to be involved in is in the Chesapeake Bay, we have expert panels that review a lot of the technology in terms of urban stormwater. And a lot of our staff are on these expert panels to kind of say, hey, so here's stream restoration, here's all the research that has happened in the last 20 years. What does that mean in terms of nutrient reduction? What can you actually claim, and how do you claim it? How do you track it? And in the Chesapeake Bay, it's much more about I think the saying they like to use is counting beans. It's much more about the little things that you do, and you're like take a literal pound of nitrogen removed is what you're calculating. Let's see. So yes, that's the background about the center. So I'm going to be talking about the Chesapeake Bay. For those that don't know, it's on the East Coast. In 2010, the EPA came out with the Chesapeake Bay TMDL, and we didn't talk much about TMDLs during this conference. It's a guidance on how much pollutant load you're allowed to have. It's based off of the 303D list. And the Chesapeake Bay TMDL is very unique because it covers 6 states and DC. Usually it's like a watershed here and there, but this is a massive, I think it's the largest one. And it covers nitrogen, phosphorus, and sediment. And with the baseline year of 2009, there's the reduction of 25, 24, and 20% by 2025. And we talked about, we talked a little bit about nitrogen and phosphorus throughout this conference, but I wanted to explain why it's an issue. A lot of times we intrinsically know that it's a problem, but why is it actually a problem? So nitrogen and phosphorus is natural, it's in our environment, and it's used as fertilizer. And we know that it causes dead zones and algal blooms, but what's happening is it's basically a buffet for algae. The algae will eat up the nitrogen and phosphorus just like your plant would with any fertilizer, and it causes these algal blooms. And some algal blooms can be very gross looking, but it itself is not necessarily harmful. Some algal blooms have harmful pieces with it. They are toxic and they do kill nature. But the actual algal blooms that happen, a lot of times the reason why it is bad for the environment is because when algae die, all this algae sinks to the bottom of your river or lake or whatever, and it's the bacteria that break down that algae. It sucks up all of the oxygen. It uses oxygen to break down the break down the dead algae, and it sucks up all of the oxygen from the water column and basically creates a dead zone. So what happens is fish is happily swimming and hits this dead zone and basically just suffocates. And it creates these fish kills like in the picture on the left. And so that's why nitrogen and phosphorus is a huge issue when it comes to water quality. And the TMDLs are all based off of, what is it called? Your swimmable, fishable, drinkable. Because it's part of the Clean Water Act. And the fishable part and the macroinvertebrates and the stream health is actually an extremely important part in a TMDL. And so, again, one of the reasons why nitrogen, phosphorus, and sediment, and we typically just call them nutrients, is a huge issue in the Chesapeake Bay. We talked about this, 6 states and DC. Here's a little map of the Chesapeake Bay watershed. The collaboration process involved in this Chesapeake TMDL is very stressful, but actually an amazing feat that the EPA has done and the Chesapeake Bay program. So within these 6 states and DCs, there's actually 5 sectors that everything is kind of divided into. Let me see here. Let me go back real quick. Sorry, I did the mini weights too early. There's 5 sectors that it is divided into. So the nitrogen reduction divided into agriculture, natural, septic, stormwater, and wastewater. And this is very unique, I think, to the Chesapeake Bay. And what I'm going to focus in on is stormwater, because that's where urban sits. So a lot of what happens and how you regulate it is in this stormwater piece, and it's urban stormwater. So it's regulated through the MS4 program. And then this graph here is the actual nutrient load allowed, that is planned, I guess. So the first column is the 2017 load, and then the gray one on the right is the 2025 target. So it's up to Maryland to decide, there's this target that EPA gives you. It's up to Maryland to decide where in each sector and where in each watershed that reduction is actually happening. And how they calculate this pollutant load is through this thing called the CAST model. I actually don't know what it's. It's Chesapeake Bay something, something tool. And this CAST model is some really, really smart modelers put together to estimate the pollutant load out of every watershed. And it's based off of every watershed, and every watershed has the whole Chesapeake Bay is mapped out with their land use and their expected contributing nitrogen, phosphorus, and sediment load. So a lot of math goes in there and outputs something, and then the counties have to meet these regulations. So on top of the Chesapeake Bay TMDL, there's a lot of local TMDLs as well. Like there's a trash TMDL, chloride, road salts, temperature, and there's just a lot of other bacteria like you guys have, a lot of other TMDLs that kind of push these stormwater regulations. And one of the things that I think is really unique to you guys, versus the Chesapeake Bay, is this whole protect versus restore idea. I think, was it, I don't remember who had mentioned it, but someone mentioned it, and was Travis when he was talking about the ag stuff and how it's so much cheaper to fix something that hasn't been ruined beforehand. And I think that in the Chesapeake Bay, especially in the urban world, we're a really old area, old city, and everything is restoring. There's not really much we're protecting. We might think we're protecting this forest, but probably 100 years ago, that forest was farmland. And so the idea for you guys to protect something before you ruin it, I think is just such a smart thing to do, to think about in the beginning, because we didn't think about that 100 years ago when we were developing everything. And I think that it saves so much money and saves the environment a lot by protecting something rather than messing it up and then trying to fix it. The mini wheats thing, save some of the mini wheats. So next I'm gonna go into DC stormwater regulations. So DC is very different than Northwest Arkansas. It's 43% impervious area. It is a phase 1 MS4. It is also a mix of MS4 and combined sewer. So it's about 2/3 MS4 and 1/3 combined sewer. And in the combined sewer, like Henderson talked about, that is managed through their consent decree, and green infrastructure is required through that consent decree, but that is separate from the MS4 permit. And so in the MS4 permit, I am an engineer, so I included some equations. You don't have to understand them. If you really want to understand them, everything is in the Stormwater Guidebook, which is in the DOE website. So DOE, the District Department of Energy and Environment, manages the MS4 program, and DC Water manages the combined sewer program. So they're two separate organizations, which gets a little bit confusing. So for the stormwater regulations, the retention requirement is if there's land disturbance or substantial improvement more than 5,000 square feet, you have to retain 0.8 or 1.2 inches of that stormwater per square foot. There's a little asterisk because there's a lot of caveats with DC. There's a lot of little nuances about this rule, but I just simplified it because it's not super important in this presentation. So that equation there is kind of how you calculate it. It is based off of the runoff coefficient and the size of your land disturbance. The 0.8 inches, I believe it's the 85th percentile storm. The 1.2 inch is the 90th percentile. So 90% of storms are 1.2 inch or smaller. So you are retaining 90% of storms in DC. There is also a detention requirement. So the difference between retention and detention, the way that I remember it is detention, like if you're in school and you get stuck in detention, you get held back for a little bit, but you always get released. So detention is a hold for a short amount of time, but you'll always go back out. Retention is kind of you're taking it in and calling it a day, like it's gone. And in DC, the model is very much based off the runoff reduction model that once you shove it in the ground, that pollutant is gone. Whether or not that's true, we can debate. But that's kind of how the requirement the numbers come from. So for the detention requirements, which is for land disturbance, the curve number of your design has to be equal to or less than the 2-year pre-development curve number, and then the curve number for your 15-year storm has to be less than or equal to the pre-project curve number. I added this slide because Andy talked about quantity control and BMPs and requiring both things and it not being integrated into one calculation. In Maryland and in DC, there's different methods of how they incorporate BMPs into their quantity control. I'm not gonna go into detail about the exact math of these two things, but they're all based off of a curve number and changing your curve number. So you have this, your existing curve number and then your post-construction curve number. It's to decrease this curve number by a little bit based on the storage you have with your BMP. So then you have this difference that you have to account for. So here is a list of approved BMPs in DC. Again, I want to emphasize that these are for MS4 regulations. For the TMDL, it's something slightly different because TMDLs don't just cover urban stormwater. In the Chesapeake Bay, you can also have restoration projects, which are not technically part of your MS4 program, to meet your TMDL goals. So what I'm talking about here is specifically for your MS4 Bmps. And there's bioretention, green roof, rainwater harvesting, permeable pavement, but I'm just gonna focus in on bioretention because I only have 30 minutes left. So what exactly is a bioretention? Sometimes it's called rain gardens, sometimes it's called bioswales, biofilters, biofiltration. The previous speaker called it stormwater control measures. In DC, we call them best management practices, and we're probably gonna change that name because of the problem with the word best, but that's what I call them, so that's what we're calling them here. So bioretention, basically all of these things are somewhat similar. It's a depression in the ground, it has plants, and there is some sort of soil media that allows for infiltration. And it may have an underdrain and it may have a gravel layer. So the plants are really important in a bioretention. It's just part of the bio part of bioretention. The plants have multiple purposes. One, it sucks up the water, which in turn sucks up the nitrogen and phosphorus. A lot of that's dissolved in the water. And uses it as fertilizer. And so the plants suck up the nutrients, aka the pollutants of concern in the Chesapeake, and then that water evapotranspirates back into the water cycle. So it kind of removes that water from the stormwater system. And then the roots also allow for basically keeping the soils fluffy, because compaction is a big issue when it comes to bioretention maintenance. Once that soil gets compacted, water can't filter through, right? And so the plants and the plant roots help keep it nice and fluffy and water still able to move through the water column. And the plants also, plants are amazing. They have different root exudates and mycorrhizal zones and the fungus that grows around them. All of that is able to break down a lot of the pollutants of concern, and not just nitrogen and phosphorus. There's research out there about it breaking down heavy metals and PCBs and a lot of other pollutants of concern as well. So water enters the bioretention, and the best case scenario, it can exfiltrate. That water that goes in the bioretention will seep into your existing soils and kind of disappear from the stormwater system. It doesn't technically disappear, right? But that's kind of how the runoff reduction model in the Chesapeake Bay works. And whatever doesn't, there's typically, if there is an underdrain, whatever is filtered through, it should be cleaner water, and that goes back into your stormwater system. So a really good comparison to bioretention for those, if you want to explain it to the public, is comparing it to a Brita filter. There's this ponding area where water has to enter. The reason why there's ponding is because you know that when you pour water into a Brita filter, it goes slower through the filter, right? So there has to be a way for water to store there to kind of like hold it for a little bit to allow the water to enter that filter and come out cleaner. It's increasing the retention time to allow for pollutant removal in the filter layer. And then there's your filter. A lot of stuff is happening in there. And it can't just kind of flush straight through because it does need time for the soil particles to do whatever reaction it needs to, whether it's absorption, adsorption, just simply filtering it, holding back some of the larger pieces of sediment, whatever it is, some time needs to pass for that water to trickle through and be clean from the filter media. And then cleaner water comes out the other end, just like in a bioretention. The cleaner water can either exfiltrate into the ground or come out of the storm drain or the underdrain into the storm drain pipe. Oh, and it also has to leave the system as cleaner water. So, great, water has disappeared. What actually happens? Like, is that blue piece of water actually cleaner? There's a lot of research out there that has been done to measure what your actual removal efficiencies are. And I will say that, your removal efficiencies and how it was tested in, Minnesota does a lot of work, and Ohio State, and a lot of Kentucky, and there's just a lot of schools that do bioretention performance research. The reduction number is really based on how it was designed. And it's always hard for me to say, oh, it's 75%, because it really depends on what your design criteria are and how it was designed when you were testing it in the lab. So one example I pulled out is Minnesota Stormwater Manual, and they provide percentages or recommended pollutant removal efficiencies. But again, it really depends on how it was designed. And I think these removal efficiencies are based on Minnesota's design requirements. And so the way that DC kind of gets out of doing this kind of calculation and really thinking about the removal efficiencies is that they just base everything off of the retention volume. So that volume that gets sucked into the ground, we're saying that it's 100% removal efficiency rate because it's in the sense of the bioretention and out the storm drain pipe, the water's not there anymore. So this chart was not meant for you to read, it's just meant for being overwhelming, that there's a million different guidebooks out there and different design criteria, and it just varies a lot based on what year it was published, because there is so much research out there, and every year we're changing what we think about bioretention and what works and what doesn't work. And it's also one of the important things is that it really depends on your pollutant of concern. Taking a stormwater manual from California, they might not care about nitrogen and phosphorus nearly as much as the Chesapeake Bay does, or you guys might not care about nitrogen and phosphorus. I know you guys do, but let's just say every state and every jurisdiction and every water body has different concerns, and to have an overarching design criteria, I think doesn't fit with how bioretentions are designed. So I just want to point that out, that there is no one right answer in terms of design criteria, but I will talk about DC's design criteria just to give you an idea. When you break it down, every criteria item, there's a reason for it, and I can probably tell you the reason for almost every single one of these and why it is the number that it is for DC. So it's really important to think about when you're looking at your design criteria, why was that number created? And DC and the Bay Area tend to be a little bit more picky about these details than some other states might be, so you don't want to add undue requirements for reasons that you might not care about, that might not be important to your water body. So, DC's bioretention design criteria. One of the first questions to ask is there infiltration into your native soils? In DC, we call it infiltration, but a lot of places it's called exfiltration because you're leaving the system. Best case scenario is you have some nice sandy soils and water just kind of trickles down into the ground. Not typical in DC. It's very, very urban. Everything is redevelopment. And so a lot of the times, I would probably say 50 to 75% of plans that I see are standard design because there is no infiltration into the native soils. So if it does have infiltration, it's enhanced. If it doesn't, it's standard. It's kind of how, in Virginia or Nashville and Fayetteville, there's a level 1 and level 2. It's kind of that idea of, there's a higher standard for better infiltration systems. And an infiltration test is required in DC. So I'm just going to go through really quickly some of the design guidances. Ponding, 3 to 18 inches. Filter media, depends if it's standard or enhanced. And the filter media depth is really about, in the end, the retention time, the amount of, you need a longer system, just like your Brita filter, right? If you want it to retain for longer and water to have a longer time of concentration, time passing through all of the different medias, because that way the filter media has the ability to absorb some of the pollutants in the water. In the filter media composition, typically a lot of times it's mostly sand and very little organic content. The organic content percentage really varies a lot depending on what jurisdiction you're in. In DC, we don't allow for high organic content because nutrient is the pollutant. So if you have high organic content, you're just repolluting your water. So that's one of the reasons why. And there is a lot of debate about this because super sandy soils, low organic content, does not make a good space for plants to survive. So, we always want to say, we want to plant native species in our bioretention and have pollinators, but these aren't native soil types. They're not happy places for plants. So we have to be very strategic about what type of plants we put into a bioretention and make sure that they survive with these filter media requirements. So next, some more calculations. How does DC calculate their storage volume? This is it's designed like a planter box, basically. Here's the equation, but I'll break it down. It's very, very simple. It's basically the volume of ponding that you have, plus the volume of the filter media times 0.25, which is the porosity of the filter media. So that's the little pore space. 25% of that volume box of filter media can be filled with water. And then below that is the gravel, and that porosity is 0.4. So in a box of gravel, 0.4% or 40% of the space is airspace that can be filled with water. You add all those up, and that is your storage volume, almost. So that is technically your storage volume, but for enhanced, you are allowed to account for 100% of your storage volume. For standard, you account for 60% of your storage volume. So that's just saying, a standard is not going to perform quite as well because there's no infiltration into the existing, so you only get 60% of your storage volume. Let's see here. So that's kind of the summary of DC bioretention and DC regulations. There's a lot more. I can talk, we have a training for this and it's like 6 hours long. So I really distilled, I think, the important stuff that you guys might be interested in. But they are free trainings at DOE websites on the DOE website if you want to learn more about how DC calculates their stormwater retention requirements. So I just wanted to throw in some examples of practices that we've put in. And I did focus in on a little bit more on detention ponds, because I know you guys have a lot of those that are failing. And so at the center, we mostly work in the restoration realm. We don't work with new developments. We are a nonprofit. And so in Maryland, it's a lot, in DC, it's a lot more about restoration, because everything's already developed. So to meet their TMDL goals, a lot of practices have to be put in, in somewhere that's already existing. Some existing parking lot or school or field is where we were putting in a lot of the stormwater BMPs. So for this specific project, it was an existing dry pond in a church. And this is pre-construction, but I couldn't find the pre-construction picture, so technically this is right during construction. But it is a dry pond, and those two little concrete pieces are the inlets into the pond. And this is what it looks like afterwards. It looks very, very similar, but it's actually a bioretention underneath. We added these, the little white gravel is allowing for pretreatment, and I think I have another slide about it, but pretreatment we found that is extremely important in bioretention design. I think Ted mentioned how their bioretention maintenance, what did he say, like 5 or 10 years, he would have to dig up the filter media and replace it. We've learned that if you add a pretreatment system, and it can be as simple as like a little triangle of your bioretention, or I personally have started design more in as some might not like it, but I build like a little concrete pre-treatment because maintenance is so much easier in concrete than trying to clean out grass or those little gravel pieces. Trying to clean out sediment between riprap is really hard. So we want to make everything easier for the maintenance team. So I personally like having like a concrete, little concrete path that can hold back some of that sediment so that they can literally just take a flat edge shovel and take it out, all that sediment that builds up there. And obviously it depends on what your drainage area is, whether or not you even have a sediment problem. If there's a very low sediment load place, then it's not nearly as important. Let's see. We did design it with a turf bottom because of the maintenance reason. There's a lot of science behind, or research behind, what is best to be planted in a bioretention. And from a maintenance perspective, it's whatever's easiest. I hate saying that because I know how important plants are for multiple reasons, but I think research, I want to say it was in Connecticut, looked at bioretentions that were planted with turf versus bioretentions that were planted with this gorgeous native plant palette, and they found that in the long term, when you first start off, the native plant palette is a lot better. But because of the difficulty in maintenance and the likelihood of it not getting maintained or not getting maintained correctly, you start losing the infiltration rate because things get compacted. You lose storage volume because your plant roots are just kind of going crazy inside where you should be storing water. And they found that the infiltration rate in turf grass being mowed by their maintenance staff ends up being equal to or better than infiltration, better than a planting, a native planting mix. So that is not saying that you should plant everything with turf grass. Just saying that you have to think about maintenance when you're designing these systems, and if you don't think that their maintenance is going to be done well, and especially when it's a restorative project and the maintenance goes to this church. And we know our community and we talk to the landowner to understand what their capacities are. And we just found that turf grass was just a lot easier for them. I'm gonna skip some of those things. And then unfortunately, we found some humongous boulders while we were excavating this project. But thankfully, EQR, who was the contractor who built this, was doing some stream restoration projects nearby. So they just took these huge rocks and shipped it to their stream restoration site, which is perfect for us. It would have been very expensive to get rid of those things. Oh, one other thing is that 2 years ago, I think it was 2019, we wrote a guide for retrofitting stormwater ponds on private lands. I actually didn't know about this, Leif, until we talked to you guys. I was like, let me look at what we've done. And so it is about those HOAs that haven't managed their stormwater ponds and what to do with it and how to prioritize it and kind of what should be done to revitalize a lot of these stormwater practices. And in Maryland, our baseline for our TMDL is based on 2009. So if the stormwater practice was either already not functioning at 2009 or you make improvements on it, basically that difference, the improvement that you make on it, you can account for your TMDL, which is why retrofitting, since you don't have to deal with the landowner piece of it, is popular in, retrofitting ponds is popular in the Chesapeake Bay area. All right, so some quick lessons learned. When I was practicing this, I was like, most of these lessons learned are because of maintenance. Like the things that we do to design these and figure these things out, it has so much to do with maintenance because it is extremely important. When we talk about siting it, having the community and landowner engagement is extremely important. It's one of those things where we think we know what's best, but we don't. And so making sure that the community understands well what's going on is super helpful. Let's get that one. Utilities, I hate utilities. Again, because in the DC, Maryland area, everything's been developed. There are utilities everywhere. There's really old utilities that no one knows about. I've hit so many lines during construction, not me personally, but it's a nightmare. But you have to do the best you can. And typically, if I'm like, there's a utility there, I'm like, I'm not building anything over there. when you're designing a BMP, I guess I'm talking more specifically here about bioretention. I've started not designing with a mulch cover anymore, because what happens when you add mulch to your beautiful bioretention, basically when the first time it rains, all that hard shredded mulch just kind of floats up and out into your overflow, into your storm drain, and clogs your storm drain. It is very important for trees. I don't design that much with trees either, because we've learned that, trees with extensive roots can break your underdrain. So if you don't have an underdrain, I think that's fine, but it can really break and clog your underdrain, and then that gets expensive to fix. So a lot of times we plant with dense, short grass covers, and some people have done stone as well. Stone gets a little bit expensive though. Pre-treatment is extremely important in a bioretention, especially if you have a high sediment load area. This one is really for maintenance. If you have a pre-treatment section that kind of the initial stuff that comes in gets held here, and then a little bit less of it goes into your next, let's just say cell, like you have 2 cells, it's a lot easier to maintain a smaller area, and that area doesn't need to be a bioretention. It can be a grassy area that you plant, or again, I like using concrete. It's not the best because we want to decrease impervious surface, but you have to do some things to make it actually function correctly. So that pre-treatment allows for that first sediment load to kind of be concentrated in the first section, so your actual expensive BMP lasts longer. And then a simple planting pallet. Even with a native pallet, having a simple planting pallet is very advantageous, especially for communities that might not have experts or might not have the ability to hire experts. Having a guide that has your 10 plants, 5 plants, and say what it should look like, when you should cut them, what they look like in the winter, in the summer, in the fall, the spring, and what needs to be done, I think is a really good way to have your planting palette done. But if your community loves landscaping and loves flowers and pretty vegetation, then you can have a more complex planting palette. It really depends on who you're working with. I'm just gonna skip through this because of time. Maintenance. Having a set routine maintenance and making sure that it's communicated with the community or whoever you're working with is extremely important. The maintenance of the vegetation and sediment to keep the function of your BMP. And then there is a difference between routine maintenance and restorative maintenance. Routine maintenance is it's like changing your oil. Restorative maintenance is like replacing your engine. And we want to avoid restorative maintenance because it gets really expensive. And this has happened a lot in Maryland, where a BMP completely fails in 5 years because there is no maintenance, and the plan was for 30. And EPA comes in and it's like, well, this isn't working. You can't account for this. So you have to replace the whole thing to make sure that it's working correctly. And then again, training of all of these things is extremely important as well. You get trained on how to lay pipes. You should get trained on how to maintain a BMP. And then one of the really important things is that this is an iterative process. The things that you learn through maintenance, you should kind of bring back to your engineers and designers and construction crew to kind of make those changes to make everything easier. And having open communication between all of your partners is really important for a working BMP. Okay, so bonus slides. I was talking about the bioretention, but through the conversations, the presentations yesterday, and with conversations with Leif and Morgan, I added regenerative stormwater conveyance systems into this presentation, because I thought that they seem like something that you guys might have, it might be useful for you in these. It's a fairly new stormwater BMP. It's developed in Anne Arundel County in Maryland. They're also called step pool conveyance systems or coastal plain outfalls. It's really a method to restore an eroding channel through a series of pools that can help dissipate energy, stabilize conveyance, and provide some treatment. It's typically designed for the 100-year storm. So what is a regenerative stormwater conveyance system? We have a cross-section here and then a plan view. There are a bunch of riffles and cobbles and boulders involved that allow for energy dissipation and to decrease velocity. And then underneath there's a sand wood chip layer that allows for infiltration of that water, and so some water quality treatment. And then these pools allow for some sedimentation, some energy dissipation, and habitat and water quality benefits as well. In the picture is not included is there's usually vegetation around that again provides the water quality benefits, habitat, and stability, and root wads, same thing. So you see on the bottom picture, there's a bunch of pools and riffles, and so each one kind of the water cascades down and allows to dissipate some of that energy, and eventually, typically, the way that the center designs them, it ends up into a stream. Just some images of what the riffles and cascades look like. Cascades, they're basically like a cascade is a mini waterfall to allow for that energy of the stormwater to dissipate as it's coming down. So this is very popular at the end of an outfall pipe. You have this huge outfall pipe that I saw a bunch of pictures yesterday with a lot of water coming through, and in Maryland, we would put in this RSC to dissipate that energy and reconnect it to a stream, right? There might be this stream restoration project that is planned that might be gorgeous and you know, reconnect to the floodplain and create all this habitat. But then you have this outfall right next to it. And, you know, how do you connect that super urban setting to this natural setting? And that's kind of where we use RSCs to connect your super urban to, or just any urban really, to the natural systems that we might be designing. There's a lot of guidance out there. The Anne Arundel County has a great one. They have this complicated but very useful calculator tool to make sure that you're sizing this correctly, because those pipes, you know, there is a lot of water coming out of those pipes, and you want to make sure that however you designed it, it's not going to blow out, you know, in your 10-year storm. And then West Virginia also has this in their stormwater guidebook as well, which we helped write. Okay, I think I already talked about this. So this is a picture of where one of our site visits that we did and where we decided to put in an RSC. My colleague there in the blue hat, we call these tiger pits usually. And a lot of times, especially in Maryland and like older streams, the stormwater outfalls I mean, you guys know it, have been cutting away at the stream banks, you know, the rock on the right, there's a pipe like around that turn that's coming out. That rock was put there by the maintenance staff to try to stop this head cut from happening, and it really wasn't helping that much. I think the water just ended up going around it. And so these are kind of places where we decide to put RSCs. So here's a picture of the post-restoration. There is let's see here. So there's the parking lot in the back, and then we connect that parking lot, so this very impervious urban area, put it through the RSC to slow down the water, to really infiltrate some of that water into the stream bank to slow it down. And then it gets released into this stream restoration piece there. And it was, the center designed it, and Ecotone, who is one of our partners, construction partners, designed the stream restoration site. And they are very supportive of beavers. They love creating habitat for beavers, so I was going to tell him that beavers were mentioned at this conference. He would be very excited. He likes to say it's our first engineers. So let's see. This is the same project, but kind of zoomed in on the before and after. The pipe is where my colleague is. It's a little bit to the right of her. And you can see the fence is the same. So that original pipe kept cutting down into the gully, and so we had to lift the bottom of the gully, and the whole floodplain for the stream restoration, or the whole stream was lifted to reconnect to the floodplain anyways. But you have to do a lot of cutting, because with really high flows, one of the ways to dissipate energy is to make it wider. So we widened the outfall to allow for that energy dissipation. Really quickly, another RSC project, there was a fire pond in the town of Newmarket. It was no longer a fire pond. Historically, it was used by their fire department, but they have since upgraded. So it was just kind of this green pond that the community didn't really like. And this project, I think, had a lot of community involvement and community discussion as to what they wanted this pond to turn into. And they really wanted to have a recreational area, so we ended up designing an RSC. The pond wasn't functional anymore, and they didn't need it, so then we could dewater it. And also their embankment was failing, so removing the pond itself was something that the town would have liked rather than replacing the embankment. So we put an RSC for water quality treatment in there. Again, a lot of these pictures are right after construction, so there's no like trees growing yet, so it should be very vegetated. I'm gonna skip over this, and the one on the right is a little bit better in terms of vegetation as what it should look like. It really would end up looking just like it did before with this like hidden stream channel or RSC running through it. I'm going past my time. So some additional resources that we have, we created the Better Site Design Manual in '98, so it's quite outdated, but we did update our codes and ordinance worksheet, which it talks about different codes and ordinances that cities or jurisdictions can have to reduce their stormwater impacts. There's a bunch of guidance that the center provides. But one of the other things I want to mention is that we do have a stormwater conference in April and hopefully in St. Pete, Florida. Abstracts are due, I think, in like 2 weeks if you guys are interested. Okay, and I want to thank, again, the Illinois River Watershed Partnership for hosting this conference, and I guess we'll go to questions.
Well, thank you, Carol. Questions for Carol? Yeah.
Okay. There was some early research findings from the Baltimore ecosystem study that indicated that riparian buffer zones in urban areas don't always function the way that conventional wisdom says, and that in deeply incised streams, those riparian buffers can actually become a source of nitrogen rather than a nitrogen sink because of the drying of the riparian soil. So given that nutrient loading in the Illinois River is going to continue to be a problem, and that's actually how the Watershed Partnership got started, was because of those concerns with phosphorus. What approaches do you recommend? Well, have those findings continued to be borne out? And what approaches would you recommend towards addressing those?
Good question. I am not a stream expert, so I don't know if I'm the best person to answer that question, but I do agree that there has been research that stream restoration may not, stream buffers may not always be the best for nutrients, but yeah, I don't think I can answer that question just because I'm not a stream person. So sorry. Yeah, I can put you in contact with somebody who could answer that question though. So if you write down my email, we do, as my colleagues do work on the stream restoration expert panel. They actually came out with a lot of new guidance, so maybe that might be useful about how to account for stream restoration in terms of pollutant load reductions.
Anyone else in the room have any comments on that or thoughts from stream perspective? No? Okay. All right. Other questions? Travis?
I was wondering, could you go back to your slide at the Adventist Church to either the plan view or the actual construction documents and kind of walk over what the subsurface looked like on that project?
Yeah, sure. Okay, this one. So underneath, so first layer is turf grass, and then there's 2 feet of filter media. That's that really sandy, low organic content material. and underneath that is about 3 or 4 inches of choker stone. A lot of jurisdictions allow for filter media rather than choker stone. The purpose of that is so that the filter media doesn't fall into your gravel. It's really so that your layers stay layered and they don't migrate into each other. So you have these tiny particles. These choker stones are about pea, they're also called pea gravel because they're the size of peas. A little pea gravel layer, and then you have your under drain gravel. So like I said, some jurisdictions allow for filter media instead of the choker stone. We find that filter media clogs really quickly, so we don't recommend that anymore. Sometimes in some or regulations it's still allowed. And then underneath that is a 57 stone. It should be double washed and cleaned because the fines in stones can, in the end, clog your system and become pollutants. And that 57 stone acts as a retention layer, but it originally was there to protect your underdrain because you don't want any of that filter media to clog your underdrain because in the end, a lot of times that underdrain is connected to your overflow as well and connected to your outflow, and you really don't want any of your pipes to clog because in the end, cleaning those pipes or replacing those pipes gets really expensive. So again, maintenance reason. And so then there's an underdrain that's 4 inches, sometimes it's 6 inches, that's perforated. So happens is when it rains, that water filters through all of these layers and into that underdrain layer and through the holes of that pipe, and then eventually it comes out into your storm drain. This specific design, we put an upturn elbow in. I didn't talk about upturn elbows because it gets a little bit technical, but what it does is it again increases that retention times and allow for some denitrification to happen because it creates this anaerobic condition that the bacteria that break down nitrogen, so nitrate and nitrate, and turn into nitrogen gas, thereby removing it from the water system, really likes this anaerobic condition. And so the upturn elbow kind of creates this supersaturated zone to allow for that to happen. And then so that once that water ponds up to the invert of the elbow, that water will go into that catch basin and into the storm drain.
Answer all your questions, Travis? Yeah, great.
Okay.
Thanks for that explanation. So on you mentioned maintenance and on this project, and you mentioned training in another slide. For something like this, when you do a retrofit like this, or for new construction potentially as well, do you have any kind of process or steps you go through in terms of ensuring that there's a maintenance guide plan in place?
Yeah, I mean, it depends on which jurisdiction we're working in. In Maryland, in restoration projects like this, it's with the homeowner. In Anne Arundel County, I think the previous speaker mentioned something similar. In Anne Arundel County, the landowner for restoration projects, the landowner is responsible for like the routine maintenance, but any structural maintenance that requires an engineer, the county will go in and fix. So there's kind of a shared maintenance responsibility. In DC, it is part of your covenant, so it actually goes on your deed, this BMP, so you can't just write it off when you sell your place, it's on your deed. And the homeowner is required to maintain that as part of the covenant. And in public spaces, maintenance is always an issue. But right now, they've transferred a lot of the responsibility to DOE for stormwater maintenance because they realize as a district as a whole, the piecemeal maintenance, DDOT maintaining it, Parks maintaining it, DC Water, well, actually I don't think DC Water isn't part of it, but DOE maintaining some of it, or schools maintaining some of it. They think they're trying to pull all of those resources together to have one agency deal with it and maintain the district-wide BMPs. But it's really new, like the RFP just came out. So it's a new thing that they're trying to do to hopefully make the process more efficient.
Cool. Any other? Yes, we have a question from online, our first.
Wow.
This is from Kevin Moore. Is there a way to determine whether clogging is occurring from the filter media layer or whether your system is being overwhelmed by outside sediment?
Yes. So there's a lot of checklists, and those checklists are based off of things like that. But there's multiple things. One, ponding should not, the way that it's designed, ponding should not be occurring for more than, let's just say, 3 days. If it is longer than 3 days, typically you have something wrong. Something is wrong in the system that's clogging the water from leaving. Because, right, if you picture this profile or cross-section here, water should trickle down into your underdrain and eventually leave that pipe, right? There's nothing holding it back, really, aside from clogging. So one of the things that there usually is an observation well or a clean out connected to your underdrain. And so this well goes all the way down to the bottom of your BMP. And then when you open the cap, if you see water in there and there's water ponding on top, likely there's a clogging in your pipe. But if you don't see water in there and there's ponding on the top, there's something wrong with your filter media because water isn't underneath, right? It's only stuck on the ponding area. So that's one of the indicators whether or not it's working. And actually, like, it's pretty obvious visually when when it's all algae and the sediment is very compacted, that there is clogging happening in the filter media. And another indicator is if you see kind of like the baseline of where your filter media should be, if it's lower than where it was originally, it means that it compacted. And then also if you dig in, if you take an auger and kind of look at the soil, if the soil profile changes a lot, let's just say the first like 3 inches, it looks like a completely different soil and you can tell it's very compacted, then that's probably clogging as well.
Great, thanks Kevin for that question. Any other questions? On those regenerative conveyance structures, are we doing that in Northwest Arkansas? Not that anyone's aware. Could we, you said, I think you had a guidebook or a manual on there.
Yeah.
Maybe we'll post that on the on our learning portal as well for this conference.
Yeah, and it's ever changing, the design guidance for RSCs, because it is a newer technology and we're figuring out there's better things or worse things and things we should avoid. And because it was initially designed in a very coastal community, changing it to non-coastal is also something that people are thinking about. Like, a lot of times now, instead of using those big boulders, we actually use the trees that we took down to kind of create that weir system for the pool, just to decrease the amount of waste. And also, a lot of people complain about RSCs because it's so structural. Because it's always connected to some sort of stream restoration. In stream restoration, you want it to have like natural stream design, natural channel design or whatever. And this is kind of an eyesore relative to that natural space. But we think that, you know, how else you can remove that outfall? Like, what else are you gonna do to protect your stream? So we're typically okay with the look of RSCs for our purposes. Some people put them in stream restoration inside a stream restoration project. We don't typically design like that because we don't do a whole lot of stream restoration projects. So yeah, even that is, you know, always changing.
Great, thanks. And John Pennington reminded us that Watershed Conservation Resource Center has put some of these in actually in Northwest Arkansas.
That's
so
awesome.
Thanks, John. All right, thank you, Carol. Great presentation.
Thanks.